Hi, so this is my Advanced Topics in Chemical Physics presentation. It's on a cold atom Fermi-Hubbard antiferromagnet, which is a letter in Nature. In this paper, the authors realise a cold atom antiferromagnet, and they investigate what happens to the long-range magnetic order when they change the temperature or when they dope the magnet away from the half-filled state. The model that they're working within is the Hubbard model, which describes low temperature antiferromagnets quite well. And the parameters that they measure are the spin structure factor, the correlation length, and the staggered magnetization of the system, which all describe the strength of the magnetic order and how long range it is. They do this experimentally using a high-resolution microscope. The Hubbard model is difficult to simulate in the doped regime owing to the fermion sign problem, which is the problem of numerically evaluating the integral of a highly oscillatory function. This is because the wave function changes sign when any two fermions are interchanged, because their wave functions are antisymmetric. The authors find that the antiferromagnetic order is stronger at lower temperatures for constant doping, and that magnetic correlations in the system persist even up to dopings of 15% at constant temperature. The Hogwart Hamiltonian is a fundamental model for spin half-lattice electrons. It's a simple way to get insight into how electronic interactions in a strongly correlated system give rise to insulating, magnetic, and even superconducting effects in solids. It came about in the early 1960s because of transition metal monoxides such as iron oxide, nickel oxide, cobalt oxide, which are antiferromagnetic insulators, but by methods which treat strong interactions less carefully. They'd originally been predicted to be metallic, and the Hogwart Hamiltonian was developed as an alternative model. Since then, it's been applied to systems like heavy fermions and the cerium volume collapse in the 1980s, to high temperature superconductors in the 1990s. So it's quite a useful, wide-ranging model with a lot of applications. So this is the Hubbard model. The Hamiltonian describes a competition between kinetic energy, T, and interaction energy, U. It's written in terms of fermion creation and annihilation operators, C and C dagger, different from A and A dagger for the harmonic oscillator. Conceptually, the biggest difference is that they're not expressed in terms of momentum and position operators, but rather just exist on their own. The subscripts J and sigma are site and spin indices respectively, so C dagger creates a fermion of spin sigma at site J. The occupation number states are no longer just N, but they are instead described by a collection of occupation numbers Nj sigma, expressed as, say, N1 up, N2 up, N3 up, N1 down, N2 down, N3 down, etc. So now that we understand the characteristics of the fermion creation and annihilation operators, we actually have to write the Hamiltonian. So to start off with, we have a regular array of nuclear positions. For simplicity, we consider these fixed. So we start from a lattice of atoms or sites on which the fermions can move. The Hogwart Hamiltonian simplifies the atoms in a solid to a collection of sites, each with a single level or orbital, which is quite a big simplification, but actually it works fine for our purpose here. And so with this simplification and with the Pauli exclusion principle, the sites are limited to one of four occupation states: wholly unoccupied, occupied with a single up fermion, with a single down fermion, or doubly occupied with one of each. As an aside, in this particular paper, the fermionic types are not actually electrons of spin up and spin down. In this case, the authors use 6 lithium atoms with 2 different hyperfine states, but for simplicity, it's easy to refer to them as up and down. The first term in the Hamiltonian is the kinetic energy term, an expression which destroys a fermion on one site and creates it on a neighbor. The energy scale T, which governs this hopping, will be determined by wave function overlap between 2 atoms. The kinetic energy term here describes the destruction of a fermion of spin sigma on site L and its creation on site J, or vice versa. The symbol with the triangle brackets under the sum emphasizes that hopping is only allowed between adjacent sites J and L. This is because the wave functions die off exponentially, so there's very little overlap between sites that aren't adjacent. The second term is the interaction term. In the Hogwart Hamiltonian, we only consider interactions between two fermions on the same site. By the Pauli exclusion principle, these have to have differing hyperfine states. Interactions are zero between fermions on different sites, and U between two fermions on the same site. And then finally, we have the chemical potential term, which controls the site filling. We refer to the situation where there's one fermion per site as half filling, since the lattice contains half as many fermions as the maximum number, which is 2 per site. This is the starting point for this paper, as it is this half-filled state which gives rise to the antiferromagnetic order at low temperatures. The authors then move away from this site by hole doping and investigate how that affects the magnetic correlations, the strength, and the long-range order. In the half-filled case, and with dominant interactions, so U over T is much greater than 1, the Hogwart model maps to the more familiar Heisenberg model, which I'm sure we've all seen. The J terms in the Heisenberg model are magnetic coupling terms between fermions on adjacent sites. In this case, Jx, Jy, Jz are all equal, and the exchange energy J equals 4T squared over U. The H term at the end refers to the external magnetic field with periodic boundary conditions. It's possible to conduct experiments with no external magnetic field, so we are actually just going to neglect that term. With negative J, we have antiferromagnetic order at low temperatures, and this long-range order persists for all finite U over T. So going back to the Hubbard model, we start in the case of half-filling with long-range antiferromagnetic order by creating a cold region of uniform density. This is predicted by both the Hubbard and Heisenberg models. The authors then hole dope away from half-filling and investigate how this affects the strength of the magnetic ordering. As we move away from half-filling, we get coupling between spin and motional degrees of freedom, which give rise to this phase diagram, which is quite difficult to understand conceptually, but it's also quite difficult to simulate numerically. Monte Carlo methods fail here due to the fermion sign problem. The red star on the diagram indicates the point of strongest magnetic order. The authors follow the trajectory of the red arrows, reducing the temperature at zero doping, and then increasing the doping from the point of strongest order at constant temperature. So it's important to understand what governs the strength of the magnetic order, given that that's what the authors of this paper are actually investigating. And the strength of global antiferromagnetic order on a bipartite lattice is quantified by the staggered magnetization, which is M. The ground state of the classical Heisenberg model on a square lattice is a perfectly ordered Néel state with M equals 1, as in it's perfectly antiferromagnetic. However, in the quantum case, we require corrections for superposition states, which reduce the energy of the many-body state. These quantum corrections decrease the staggered magnetization in the ground state to M equals around 0.61 for the S equals half Heisenberg model. The long-range order is lost in the thermodynamic limit for finite temperatures in the 2D case. This is because of the Mermin-Wagner-Holmberg theorem, which states that continuous symmetries cannot be spontaneously broken at finite temperature in systems with sufficient short-range interactions. So this means that long-range fluctuations can be created with very little energy cost, which increases the entropy of the system, so it's energetically favoured for the system to do that rather than retain long-range order. In this case, the spin correlations decay exponentially over what's called the correlation length. This grows exponentially with inverse temperature, so as the temperature increases, the spin correlation length becomes so short that you lose long-range order. However, in this paper, we're looking at a system with finite size, so we get antiferromagnetic ordering at non-zero temperatures, which is good, and the correlation length is roughly equal to the size of the system, so we do get antiferromagnetic order across the whole sample because the spin correlations don't decay away completely, even at non-zero temperature. So now I'm just going to briefly talk about how they prepared the state to perform the investigation. So they need to start by making a very low temperature sample. So the two lowest hyperfine states of lithium-6 with repulsive interactions are loaded into a 2D optical dipole trap, which reduces the temperature. They then ramp to a magnetic bias field of 576 G and perform a final stage of evaporation under the magnetic gradient, which allows them again to reach even lower temperatures. Then the bias field is removed and the lattice is loaded from the dipole trap. So we now have our optical lattice. It's then subjected to a potential from an incoherent blue detuned ring-shaped light field. And what this potential does is partition the system into a sparsely filled reservoir on either side and a densely filled central region, which you can see at the bottom of the figure there. And by partitioning the system in this way, the entropy redistribution is enhanced, and a higher fraction of the entropy is shifted to the reservoir, which reduces the temperature of the central region and gives it a nice uniform density to work with. The first part of the investigation involved changing the temperature at the half-filled state to investigate the effect of temperature on the strength of the long-range order. So the evaporation from before was chosen such that the final state achieved is at half-filling, which involves having more atoms at higher temperatures and fewer atoms at lower temperatures. The sample temperature is varied by holding the gas in the lattice, with the potential projected onto the atoms for variable time. At zero hold time, you achieve the minimum temperature. And at the coldest temperatures, which is roughly 1/10 of the Fermi temperature, we had approximately 400 atoms remaining in the trap. The second part of the investigation was to keep the atoms at constant temperature, but to change the density of the system by hole doping. And the density of the sample is varied by varying the potential that's being projected onto them. So the potential, the blue light potential that they're being subjected to is both controlled by and projected onto the atoms using what's called a digital micromirror device. So that's what they use to hold over the system. The detection method by which they're getting their results is based on selective spin removal, followed by site-resolved imaging of the remaining atomic distribution, which is all done using the microscope. So spin removal begins by increasing the lattice depth, which rapidly reduces the tunneling of the atoms. And one spin state or hyperfine state is ejected from the trap by driving cycling optical transitions for either hyperfine state with a beam. So we've got images then from where one state is removed, where neither state is removed, and where the other state is removed. And by combining all of those, you can compute the local spin correlations. For each temperature value in the temperature dataset and for each doping value in the doping dataset, 70 images were taken with no spin removed, 70 with one, and 70 with the other. So we've got a comprehensive set of data from which we can compute the spin correlation. So now we're just going to move on to the results of the investigation. The spin correlator was determined by averaging over many independent experiments. And what the spin correlator does is it compares the number of parallel and anti-parallel spin orientations on two sites, separated by a distance d, and is positive if parallel spin orientations are preferred, and it's negative if anti-parallel spin orientations are preferred. We can see in section A of the figure at the top there that for lowest temperatures, spin correlations across the entire disk alternate in sign even up to the largest distance of d equals 10. So we've got this checkerboard effect over the whole system, which is expected for a state with long-range antiferromagnetic order as it's alternating in sign across the entire sample. As the temperature increases, so as we're moving left to right across the figure, the strength of the antiferromagnetic order decreases quite rapidly until at the highest temperature there, you can see that only the nearest neighbour spin correlations remain. We've only got that clear black to white for the very centre. Section B of the figure there shows an azimuthal average of the sign-corrected spin correlator. So it's still the spin correlator, but it just shows the strength of it rather than the sign. So they're all positive. and that's as a function of distance. For larger distances, the measured correlation function scales exponentially with distance, so we've got this exponential shape there. The coldest temperature correlators are shown in the higher temperature plots as a grey line, just to demonstrate that the correlation is strongest at lower temperatures. In this 2D system, the quantum fluctuations increase the spin correlation at short distances, which is why at d equals 1, the spin correlator is just so much bigger than the rest of the plot. And from these plots, we can determine the correlation length of the sample just by fitting it to a simple exponential function. For a 2D system, we find antiferromagnetic long-range order by measuring the spin structure factor at wave vector q equals qx, qy. In a square lattice, a peak in the structure at wave vector q equals pi over a demonstrates long-range antiferromagnetic order, which is why we call that QAFM. The amplitude of this peak is related to the staggered magnetization, which is the strength of the ordering, as we discussed earlier. So if we look at section C of the figure, at the lowest temperature, we've got a sharp peak right in the center at Q equals QAFM, confirming the presence of antiferromagnetic long-range order. For increasing temperatures, the amplitude of this peak decreases, so it becomes less strongly blue in this figure, until it disappears completely, indicating the decay of long-range order at higher temperatures. At the higher temperatures, we still have a peak, but it's much broader and lower amplitude, and that just comes from the short-range correlations that still exist at these temperatures. Section D of the figure is a plot of experimentally determined correlation length as a function of temperature. This correlation length takes an exponential increase below temperatures of around T over T is 0.4. At the lowest temperatures, we find a correlation length which is roughly comparable to the size of the system, about 10 sites, which is what we wanted. We wanted to show that for really low temperatures, we get this strong antiferromagnetic order across the whole sample. Section E of the figure is a plot of the corrected staggered magnetization. So this is quantifying the antiferromagnetic long-range order, and the corrections adjust for uncorrelated contributions. The CSM increases markedly at lower temperatures, which again is what we wanted to show. So now we're just going to move on to the second part of the investigation, which is investigating the effect of doping on the magnetic order. So we're able to use Monte Carlo methods to predict behavior for half-filled systems down to very low temperatures, but this isn't possible when you dope away from half-filling. This is because the fermion sign problem scales exponentially with inverse temperature. So instead, the effect of doping on long-range order was studied experimentally by reducing the sample density and measuring the spin structure factor. So this plot here is of the spin structure factor, and again you can see at QAFM we've got a strong peak there. Up to doping of about 15%, the corrected staggered magnetization, which is shown on this plot here, decreases until it settles at an approximately constant small value after dopings of 15%. This value just comes from the short-range correlations, which still exist even at very high doping levels. And for the system in question, strong magnetic correlations persist up to a critical hole doping of about 15%. Going back to this phase diagram, which we looked at earlier, which comes from the Hubbard model, we can see that the authors have explored some of the diagram in quite good depth for what's a pretty theoretically challenging regime. So they've looked at the effect of temperature, and they've gone into the antiferromagnetic phase, and then they've kind of come out of the antiferromagnetic phase just by doping. Using the experimental methods laid out in this paper, the authors predict that even more of this phase diagram could be explored, possibly by reducing the temperature further using entropy redistribution, which they did here, but a more sophisticated entropy redistribution scheme could be utilized to get down it maybe into the pseudogap phase or to the D-wave superconducting phase. They even go on to claim that we could reach entirely novel states of matter just by augmenting the Hamiltonian with things like alternative lattice structures, because here we've used a very simple square lattice, or applying a gauge field, or using dipolar long-range interactions just to change the Hamiltonian and to see how that will affect the characteristics of the matter that we're exploring. So that's pretty much the end of the presentation. There's a few supplementary slides attached, appendices containing information which I didn't think there was time for or didn't particularly fit well in the main presentation, but I've included because I think it's interesting and because I think some of it will help to explain the physics behind the Hubbard model. So I've attached some extra information on the fermion creation and annihilation operators, the fermion sign problem, and one application of the Hubbard model, which is the Cerium volume collapse.